Hello, my name is Faisal Chaudhry, and this lab presentation is on Lab 5, Faraday's Law. To start off, the north pole of the bar magnet was found using the magnetometer in my smartphone by finding which pole of the magnet will produce a positive magnetic field in the x direction. The bar magnet was then dropped through a roll of aluminum foil 5 times to get an average fall time through the tube. Next is a short video depicting one of the trials. To get a general understanding for this lab, I based the lab on some goals, like observing how the falling magnet's velocity and duration of fall is affected by surrounding magnetic fields, as well as using Faraday's law to assess any changes in the fall given the surroundings. I assume that the air resistance in the y direction is ignored, and that the tube and magnetic field of the bar magnet are perpendicular to each other. Also, I treated the roll of aluminum as a series of loops or rings stacked on top of each other that will be used later in GlowScript. For the fundamental principles, I used the Biot-Savart law to calculate the dipole field of the falling bar magnet using the magnet's dipole moment as well as the distance from the magnet's center to the end of the tube. Also, the magnetic flux formula was used to calculate how the flux changed as the magnet fell through the tube using the magnet's velocity as well as the tube's length and radius. Also, I used the force on the wire loop and Newton's second and third laws to calculate the net force acting on the magnet as well as the change in velocity of the magnet as it fell through the tube. I measured the aluminum foil roll to be these precise measurements, which I will use later on in GlowScript. Also, I used the magnetic dipole moment of 2.5623 ampere meter squared from Lab 3, and I found the average fall time of the bar magnet to be 1.46 seconds through the tube. Now on to the code. The physical constants are set here, including the resistivity of aluminum, which will be used in the model. Also, the graph is initialized as a velocity versus time graph. This portion of code creates the aluminum foil tube in the generated model. Step 1 includes edits of the tube's actual length, width, radius, and inner radius of the hole. This portion of code creates the bar magnet using its mass and dipole moment, and the function at the bottom creates the magnetic field for the bar magnet. This function calculates the magnetic flux of the magnet through the tube using the flux formula from the fundamental principles. This simulation loop iterates through to model the bar magnet falling, and the gravitational force on the magnet is calculated along with the ring current at each specific location along the tube. And lastly, this portion of code calculates the magnetic field at each ring, the total magnetic force on the magnet, as well as the total net force acting on the magnet. The blue on top of the bar magnet in the model indicates a counterclockwise current because of the upwards magnetic flux, so the red on the bottom indicates a clockwise current. If the magnet is inverted before it falls, the only thing that will change is that the blue will be clockwise and the red will be counterclockwise. Also, there is an approximate error of about 28% between the computer model and the actual average fall time, so the computer model might be a bit more accurate for an ideal situation. And lastly, the flat part of the velocity versus time curve indicates no change in velocity or F-net of the magnet inside the tube. If the resistivity of the conductor were reduced, then the current at each ring along the tube would increase, thus increasing the magnetic force acting on the magnet. With an increase in magnetic force, the net force acting on the magnet as well as the velocity of the falling magnet would also increase, indicating that the magnet would fall faster through the tube if the resistivity of the conductor were reduced. If holes or slots were cut into the tube, then there will be a decrease in the number of rings created in the model and an overall decrease the ring current magnitude through the tube. With the decrease in ring current, the magnetic force will also decrease, which will also decrease the overall net force acting on the magnet as well as its falling velocity. Thus, The magnet will fall slower through the aluminum tube if holes were cut into the tube. Thanks for watching.